welcome again. We are very excited this year with our web conference. We have 6 wonderful presenters today. As you are listening to the conference, we would like to encourage everyone this next year to submit projects like the ones you're seeing now. We believe it's a wonderful opportunity for us to learn from each other. We are pleased today to have as our gold sponsor Keller. The connected companies of Keller in North America are uniquely positioned to handle the most complex geotechnical construction projects nationwide. By including all services in one contract, we reduce the client risk and ensure all aspects of a project are met on time and on budget. We are also pleased to have as a silver sponsor Haley and Aldrich. Haley and Aldrich is committed to delivering the value their clients need from their capital operations and environmental projects. A one-team approach allows them to draw from their 600 engineers, scientists, and constructors in nearly 30 offices for creative collaboration and expert perspectives. Since its founding in 1957, Haley and Aldrich has one goal in all that they do: deliver long-term value efficiently, no matter how straightforward or how complex the challenge. We're also pleased this year to have Hayward Baker as a silver sponsor. Hayward Baker is North America's leader in geotechnical solutions with a network of offices across North America, each with direct access to the largest geotechnical knowledge base in the industry. Hayward Baker is ready to respond with the optimal solution wherever the location, whatever the size, and whenever required. The format for our web conference today is that we will have 6 speakers. Each speaker will be taking approximately 15 minutes to make a presentation. During that presentation, if you have questions, please go to the question and answer portion of the website and ask those questions. At the end of their presentation, each of the presenters will be selecting questions, and they will be reading them and then answering them. We will have the presenters as shown in the order. Ruspe Moghadam is going to be our first speaker. He's going to be followed by Eric Cline and Vivek Shrestha. Then Lipton Carswell will present to us after her. Liban Afi will be a presenter, and then we'll have Michael Sibley, and finally we'll have Justin Lewis. So with that, let me introduce Ruspe. Ruspe Moghadam he joined GRL Engineers in 2016 after finalizing his doctoral studies in civil engineering at Texas Tech University, where he also served as an instructor of record. Before Texas Tech, Dr. Moghadam worked as a geotechnical engineering practitioner with Bureau Veritas North America in the United States, Mexico, and Central America. His research and more than a decade of professional experience have included a significant focus on underground structures, deep foundation design in soft clays, and load resistance factor design of deep foundations. He is a member of the Deep Foundation Institute, the Mexican Society of Geotechnical Engineers, and the American Society of Civil Engineers, with active participation in the Geo-Institute's technical committees. We'll turn the time over now to Ruspe.
Here, and thanks to Geo-Institute and the Earth Attending Structure Technical Committee for organizing make it happen. I would like to present today a case that we worked on in Mexico City, and primarily involved some excavation diaphragm walls, and the main challenge there was the presence of non-controlled fill material that had been accumulated for significant years. So with that, I like to basically talk about some tasks. We refer to them as general tasks, but these were steps or sections that we had to go through in order to get information and finalize design and then get involved during the construction. One of the important tasks was to obviously have a good understanding and do a thorough work on the background, what was in the project site prior to this project. And I will show some slides eventually showing the background and why this non-controlled fill material existed in this site. We'll talk about geotechnical exploration and site characterizations and some of the challenges we faced during that those works there, and geotech lab and programming the testing, finalizing the testing, and getting some design parameters to do the geotechnical design, and further adjusting those designs during constructions and adjusting the construction procedure while executing the construction phase. And at the end, we will call it the end of geotechnical construction, and then the superstructure, et cetera, will come in. A little bit about the project is overall consisted of 2 towers. You can see on the screen Tower A to the right, Tower B to the left, if you're looking at the screen. Tower A had 26 floors, and Tower B was designed for 12. Both were going to share an 8 basement levels for parking spaces. This is located in outside of Mexico City, to the west of Mexico City, in a region called Santa Fe, which back in the days it was used as a dump, basically. Like any construction debris, any material, it was just taken out because this region was considered outside of the city, and then they will place this non-controlled fill. So basically, if we look at this arrangement, we can see Tower A, Tower B, same arrangement, Tower A to the right, Tower B to the left. And there is a main artery crossing the east side of the project site. The north is pointed to the right of the screen, so to the east side, it was a major artery or a major highway extension that it was built in the 1990s, and now this new project was near this major interstate, or the equivalent of interstate in Mexico City, and there are major restrictions on obviously displacements and lateral movements, et cetera. So if we look at the background, so there is an aerial photo showing the project site during the 1970s. And as a reference, I have put a red dotted rectangle on top. That is the original Mexico-Toluca state road, or the road that existed between these two cities. And we're going to take that one as a reference. So the project site is shown with a circle with red and white stripes. And the north, we're going to follow that north at all time. So if we go from 1970s to the 1990s, what we're going to see is a major development happening nearby the project site. So prior to that, this region was abandoned. So 20 years before 1990s, in the 70s, this place was used just for accumulation of a non-controlled fill materials and basically bringing it from the city and place it without any controlling in placement or in the material classification. As you can see here on the east or southeast of the project site, there is the new highway. That's the new interstate, or the federal highway, as it's called in Mexico, that it was passing by the project site. So in the 2000s, they decided to develop this site, And you can see it in the aerial photo for the projects that it is completed in 2006. And this is how it looks like from 2006 on forward. So basically, this was what we gathered, obviously, with the law of details, but due to time constraint and being a presentation, we have left those details out. But I will basically bring them on when I talk about the design and the testing side. So if we look at the site again, we went through a process of doing geotechnical exploration. We selected 7 standard penetration tests, or SPTs, 4 open shaft exploration, and 45 just flight auger tests just to see what it comes to the surface. Obviously, we did have access to another 15 standard penetration tests that had been done in the past. And so those information were gathered, and basically based on the existing information and the new exploration, we were able to classify the material. However, what is important to mention, the challenge here wasn't not much classifying the subsurface. It is an important fact to understand what we have underneath before we start the excavation, but assigning parameters and design parameters, selecting design parameters for this purpose was a major challenge. And on top of that, knowing how far extends down these fill material was also another challenge and another important fact for the excavation project. So we've selected some representative borings. I can talk about the majority of borings came the same. The results were the same. However, the elevations would change, obviously, as we moved from the north end to the south end. This fill material had less thickness and less thickness. I will show it in a couple of slides forward. How did we classify the non-controlled fill material thickness? So we can look at these borings. We have primarily medium coarse sand, some clay, construction debris up to 5 meters, and followed by sand and silt, clay mixed with construction debris, plastic material up to 19, 20 meters. And after that, to 26.4 meters, we had, again, construction debris, clay brick fragments, gravel, and sand and silt mixed. And at the end, the blue sand, or the blue dense sand, is a silty sand with less than 4% fines, dense, classified dense. And this is very typical of the region. So that blue sand is considered the natural geomaterial at the site, or the first layer of the natural sand. Now, these openings were generated, as I showed in the previous aerial photos. These were generated because they were exploiting this sands back in the 70s and 80s. So they created the mines, and then they filled them up with the non-controlled fill material. So if we look at the blow counts, blow counts that shows 50 or for 6 inches, or 50 for 12 inches, 50 for 0 inches, basically is showing some refusal. In the transition zone is expected because we start to see the blue sand. This is talking about the slide to the right. But in the debris material, the blow counts are all over. We have a couple of places, as shown by this red rectangles, that they had blow counts that they were 50 or plus. But at the same time, if we move a little bit to the left, we see the low blow counts, medium blow counts, so they're all over. Water content. You see the water content. I don't know if the scale is visible, but it's that dotted blue line is at 15% water content. Towards 19, 20 meters goes a little bit up to about 20, and right before 24 meters, it goes about 35%, which is a result of rain. It's not anything related to the natural groundwater or moisture content. It's just the moisture content that has been accumulated throughout the years. Once we get after like 26, 25 meters, we had almost zero water content, very dry and almost negligible, we're going to call it, water content. So based on these borings, obviously we had about 19, 20, 21 SPTs, and between the existing ones and the new ones we did, and we were able to look at the samples, send it to the lab for some index testing and some strength testing. But on top of that, we did some exploration shafts. These were like 4 feet diameter, stabilized shafts, vertical, open. And the purpose was just open the shaft, go inside, obviously with certain restrictions on the local authorities, but we were able to do a visual inspection, as you can see to the left. That is from the protection around the perimeter of the shaft, we were able to open and look at the material. And on top of that, to the right, you can see a couple of pictures of the material that was coming out from the auger, the flight auger testing. So we can see there is all different type of materials. There is different type of construction debris, plastic, even there's a shoe there, I guess. So it was a challenge at that point to how do we classify this? Do we assign design parameters based on SPT? Do we assign design parameters based on lab testing? Or we just, go ahead directly and we design everything based on assumed data and do some testing, which that's what we did, and we're going to look at the data here shortly. So we got some preliminary lab report, average unit weights of 1.75 ton cubic meter. Those are the standard units used in Mexico, about 100 pounds per cubic foot, and the internal friction angle of 30 degrees, and cohesion values were negligible. I apologize for that typo. That should have been an I, not an A. And we considered a surcharge of 0.75 times square meter, or 150 pounds per square foot, for the design process. And with that and the results of the boring, we started looking at the thickness of this fill material and how would we approach the design by sections. So now we're going to look at Tower A to the left, because now we're looking at the future diaphragm wall, at the design of the diaphragm wall. Now Tower A is to our left and Tower B is to the right. And you can see the blue material, obviously, is the blue sand. And the yellow material, the coloring, represents deeper sand deposits that they are classified as a very dense volcanic sand. And Tower A foundation solution, you can see the dotted line. We decided to go with drilled shafts, and Tower B was passing with the spread footings at certain depths of footing in the blue sand. Now, based on the results of the explorations and the SPT and the vertical shafts, what we found was that between approximately 8 and 23 meters, that's between 27 to 75, 76 feet deep, that's the non-control fill material, or unnatural soil. So the deepest thickness will be to the north, and the shallowest will be to the south, closer to Tower B. Then from there, or from that elevation, we would have a dense blue sand. And, a couple of important things to mention is the transition zone and the existence of the diaphragm wall when it goes to the transition zone. So I'm going to go on. I think I missed 15 minutes. I apologize for that. We started our design going with a horizontal pressure based on Rankine, and then redistribute the pressure using Tersaghi Peck and some of the Mexico City modified methods that existed. We designed the post-tension anchors using the FHWA or FHWA Mexico City FHWA equations to determine the bonding length, the grout steel bonding length, and the soil bonding length using the equations shown in here. And we basically distributed at 3 meter by 3 meter anchors, post-tension, and we come up with approximately 75 tons of resistance. And in order to get that resistance, since we had much uncertainties about this fill material, we decided to perform some load testing above the transition zone where it says confining wall and the diaphragm wall, and under the transition zone. So basically we installed a couple of these anchors and we tested them. Here shows the details on the testing, and performed in 2 phases. Phase 1 was to arrange the cables. We went to 25 tons and 40 tons, and phase 2 was to taking to twice the load, which was approximately 140 tons, and we get results within the 1% elongation. The total bonding length was 15 meters, the working length 15 meters, 1% of that, and the closest one was anchor test number 2 that approached that 15 centimeters on that one. And finally, some major challenges that we had to go through was obviously the transition zone. With all the different explorations we did not basically match this transition zone. So we had some places that we needed to create new confining walls to retain that bottom transition zone, and in some places the elevation presented at a different level that we had expected. During this, we had challenges, as anything else, about available information, quality and quantity of site explorations, quality of lab testing and the results, how did we select the design parameters, how did we verify this design, which was the load testing, and we had to modify certain construction process, including monitoring and instrumentation for this project. With that, again, I apologize if I went beyond the allocated time. I took the time since 12:06. If there is any question, I'll be happy to answer them. If not, my email shown on the figure will be really happy to answer your questions. Thank you.
Thank you, Ruzbe. If you have like to answer, you have a minute or two if you'd like to take that time.
Sure. One of the questions that often is asked in this situation is how much the quality of the load testing going to affect the results, and how much going to be the design verified based on the quality of testing. So, as anything else, going through a design phase, going through the boring logs and getting design parameters it's okay. We do that. There is challenges there. But then once we get to verify the design, special attention should be paid to the quality of load test. Like, how do you do the load test? How much the loading procedures? How do you take readings? Do you use different methods that exist locally, or you use methods that exist globally to determine the design load, et cetera? So this is a question that comes up usually when we have a full-scale load test involved, which it's very important to consider the quality of the load test, especially in situations like this where the soil is not completely understood or the profile is not completely understood.
Okay, well, thank you very much, Rusbe. That was a very interesting presentation.
Thank you.
Our next presenters will be Eric Cline and Vivek Shrestha. Eric is a senior manager in the geotechnical group at RK&K in Baltimore, Maryland. He graduated from Iowa State University with a Bachelor of Science in Civil Engineering and Johns Hopkins University with a Master of Science in Civil Engineering. Eric is a PE in 6 states and the District of Columbia. He was named a diplomat in geotechnical engineering for the Geo-Institute in 2009 and a fellow of ASCE in 2018. He currently chairs NCEES's Geotechnical Committee and has 33 years in geotechnical engineering, mostly in working on highway, transit, and rail and environmental projects in the Mid-Atlantic region. Vivek is a project manager in the geotechnical group at RK&K in Baltimore, Maryland. He graduated from Tribhuvan University in Nepal with a Bachelor of Engineering in Civil Engineering. He has 13 years of experience in geotechnical engineering, mostly in working in highway, transit, rail, and environmental fields in the Mid-Atlantic region. And with that, we'll turn the time over to you, Eric and Vivek.
All right, thank you, Glenn. Micropyle has been used for decades in this country to resist axial loads, even very large axial loads, but they really do not provide a lot of resistance to lateral loads, so they haven't been used too much for that. This is a pretty unique project. We only had about a 2.5-foot gap between the edge of our SOE system and active ties for a 12-foot deep excavation. And furthermore, we only had 22 feet of overhead clearance to high-voltage catenary lines. Now, 12-foot deep excavation really doesn't sound all that particularly deep, but Amtrak requires that SOE systems be designed for 150% of the Cooper E80. Now, that's equal to an 18-foot surcharge. So in other words, we had to design our SOE to be a 30-foot tall wall, but we only had 12 feet in which to place any struts or tiebacks in this case. This project is located just southwest of Wilmington, Delaware, just northwest of I-95 and I-495, and upstream of the confluence of Little Mill Creek and the Christina River. As you can tell by looking at the drainage patterns there, the area is very very flat, swampy, and outside of the swamp, it's very congested. Now, the Northeast Corridor is the main rail corridor serving intercity passenger rail between Washington, D.C. and Boston. Through Delaware, it's owned, operated, and maintained by Amtrak. But in addition to Amtrak trains, you've also got Norfolk Southern Railroad, freight traffic, the Delaware Transit Corporation, and SEPTA, the Southeast Pennsylvania Transportation Authority, have commuter passenger rail service, so it's getting very crowded. Generally, throughout most of the NEC, there's 3 tracks, but there's about a 1.5 mile long gap here in Delaware that was creating congestion. Now, the tracks in this area were first laid in the 1850s. The oldest plans we had were from 1929, and they showed the addition of electrification, the construction of a 3rd bridge, which is the purpose of this study, and repairs to the abutments and wing walls of an existing bridge that carried 2 tracks. Those existing 2 tracks that crossed Little Mill Creek were 30 feet long, and that bridge was built in 1913. This 3rd bridge, the track that carries the 3rd track, was built was built in 1929, was 54 feet long to accommodate a bend in Little Mill Creek. None of these plans indicated what the substructure or foundations were. Now, this third track was abandoned in the early 1970s because maintenance issues. That this area is a swamp, so you'd expect a lot of maintenance on embankments, but also because of reduced rail traffic, it was just no longer worth the cost to maintain the traffic. Once they decided that because of SEPTA and DTC commuter routes and increased amount of Amtrak routes, they decided to reactivate the third track. RK&K started doing some inspections on the bridge about 2004 through 2006. These inspections found that the masonry was cracked, some blocks were dislodged, and in general was in poor shape. Significantly, there was a scour hole exposing the timber piles that directly supported the timber mat that in turn supported the wing walls and abutments. We didn't know the total number of piles, but using pulse echo testing on some of those exposed piles, the piles were about 40 feet long, and based on our borings that we subsequently drilled, it extended down into continuously weathered rock or intermediate geomaterial, or IGM. Ironically, the steel girders were actually in pretty good place. Now, on that plan there, you can see at the southwest corner of the track number 2, there's a wing wall that goes to the south abutment of the third track bridge. That's going to be a significant player in this project, and BBEC will get into that in a few minutes. These photographs here illustrate a little bit better what we were up against. You can see how narrow the site was. You can see the low overhead because of the power lines for the catenary system, the cat poles, guy wires, the creek, and the scour end. You can kind of get a little bit of a sense of the condition of the masonry of the wall, of the masonry. We drilled several borings. This fence diagram here simplifies what we found. There was fill associated with the embankment. It's mostly fine-grained material, silt, low-plasticity clay, some sand, some oversized particles, about what you would typically expect. Then there was some soft to medium organic clay associated with swamps that typically where we were. Then we had some medium dense fine-grained soil, mostly sand and gravel. I think that was Cretaceous age. And that directly overlaid some continuously or completely weathered rock to bedrock. And that's where we're trying to find our foundations. As you can imagine, when you're working around railroad tracks, there's a lot of limitations. This is a quick summary of the limitations that we had. Like I said, we're 2.5 feet away from the edge of tie. This is also a safety hot spot due to the curvature of the track alignment. Fortunately, northbound trains were already starting to slow down for the Wilmington station, and the southbound trains were still accelerating out of the Wilmington station. So they weren't going their full 120 miles an hour, I think. But you can read for yourself. We had the work hours were very tight. They were about 5.5 hours per shift, and occasionally we could get the 55-hour work windows, but they were kind of erratic, and a lot of times they were pulled at the last minute. I mentioned before we had some pretty large surcharge loads. This is for the SOE at one of the abutments. Now, the dashed green line and the red line are what you typically expect from a supportive excavation system for a live construction load and the soil lateral loads. However, the black dots and the two dotted lines are for each track separately, and that solid green line is a lateral surcharge from everything we had to resist. And you can tell we're going from about a 400 pound per square foot lateral load to about 2,700 pounds per square foot lateral load. That makes a big difference. And we had to apply both loads simultaneously per REMA code. Now, Amtrak required the contract plans be detailed enough that the contractor could build the SOE without doing any design work on his own. However, they did allow the contractor to redesign to suit their own means and methods, which I think is an excellent idea. Mumford & Miller was a low-bid contractor, and they retained CCGI from Baltimore, Maryland to design and build the SOE. So all the description below is the contractor's design of the supportive excavation system. The plan view that you can see here, the north abutment had an SOE, that's to the right of the figure there. It was L-shaped because you also had to support a cat-pole foundation. And then to avoid impinging on wetlands, we had to extend the wing wall almost 300 feet from the south abutment. All those dots there you can see are the Micropyle foundations. This is an elevation. There we go. This is an elevation view of, or partial elevation view of the walls. You can see the north abutment. Micropiles were put at a 5-foot spacing, which is very similar to what our design was. To provide additional, the micropiles were a 7 5/8 inch diameter, half-inch thick wall casing made of 80 KSI steel. To provide some additional stiffness, however, what they did was he added a 5.5 inch diameter, 20-foot long casing in the upper 20 feet. And there were no joints installed on that to help improve the stiffness of the micropiles themselves. The micropiles generally were the 2-meter-long sections, 5-foot center to center. Because there were 2 rows of tiebacks and they had some pretty significant down angles, the axial load on each micropile was about 25.5 kips. And at this point, I'm going to turn this over to Bebek, and he will go into more details on the construction and the instrumentation results.
Thank you, Eric. So I'll be talking in more detail about the construction itself. This is a typical cross-section at the abutment. As you can see, we needed quite a wide section excavated to install all the micropiles for the abutment foundation, which resulted in our SOE being installed 2.5 feet from the edge of active tie. The tiebacks needed a steep angle because Amtrak required that no element would be within 4 feet of the ties. And you can see the length of the tiebacks were in excess of 60 feet. We had 15 feet of unbonded zone, and the rest, 50-plus feet of bonded zone. This next slide here is the cross-section south of the abutment where we had the retaining walls. We had a little more space in this area. The supportive excavation was about 7 feet from the edge of ties at this location. The design, however, we maintained the same design for the whole system. Now, here are some pictures during construction. This is from the south end of the supportive excavation system. Towards the south end, the wall wasn't that high, so we only had 1 row of tiebacks. You can see the micropiles for the permanent retaining walls that were already installed. For the north, towards the abutment, you can see we have 2 rows of tiebacks. The train above is an Amtrak train. That was how close the trains were running to our supportive excavation. And further north, you can see the stone masonry for the old abutment. This was during the demolition of the abutment while we were taking it out for the new abutment. Now, during construction, here's a picture of the wing wall of the existing abutment that had to be left in, that was supporting the active track. All our as-built plans showed that the wing wall was all the way to the top of the ballast. However, during construction, we found out that the walls didn't go all the way up, so we had to design a ballast stop to retain the ballast of the active track. So a contractor initially designed a system where they would install the micropiles through the stone masonry wall. However, during construction, we found that the stone masonry was just a veneer wall with rubble fill behind it. And so we designed the micropile system in front of the wing wall and put in tiebacks to support the ballast. Here's a snapshot of the instrumentation we had in and around the bridge. We had a lot of deformation monitoring points. We had some deformation monitoring points on the ties of the active track, on the soldier piles we installed, and on the catenary falls as well. There's some pictures of the instrumentation, like we had tilt plates and deformation points, like I mentioned, on the ties and on the catenary poles as well. The next slide here shows the instrumentation data we received. These are the deformation point, monitoring point data that were installed on the railroad ties. The solid lines represent the lateral movement. The dotted lines are the vertical movement. As you can see, we reached the limiting value even before we were done installing all the micropiles. So as Eric mentioned before, we had encountered during our inspection scar holes underneath the abutments. So, and Amtrak maintenance had known about this area before even construction started, and they had continuous maintenance in this area because of the scour and the loss of fill resulting in the track movement. So Amtrak would run geometry cars attached to the trains every 2 weeks to check the track profile and alignment, and ever so often they would send their maintenance crew to true the tracks using ballast stampers. The jumps you can see in the graph are, the each jump is directly correlated with when the ballast stamper came out, lifted the tracks, and tamped the ballast to true the tracks. And in around September of 2015, we were done installing the grout bags and the scour protection, and we also grouted behind the grout bags underneath the existing abutment. And after we were done doing that, you can see the movement flat-lined, indicating that all the movement happened because of the scour. And while we were doing all these measurements, we actually even went out and retested each and every tie bag, thinking that it might be creeping causing the movement, but when we tested all the tie bags, we found out that they were still working and we didn't have much creep on them. This next graph shows the lateral movement of the micropiles. As you can see, the maximum movement we measured was about 3/4 of an inch on the soldier piles. And once we were done excavating and we installed the foundation piles for the abutment and the retaining wall, the movement actually stabilized, and it flatlined, and during the rest of the construction time, we didn't see much movement in the micropiles. So in conclusion, micropiles can be used in low overhead clearance and limited access conditions. If we properly design with tie backs, they can actually support significant lateral loads. And when necessary, if you need higher section modulus, because the casing themselves don't have significant section modulus, we can use composite sections with multiple circular casing to increase the section modulus. As for the deflection of the SOE system, it is a function of the stiffness of the system, which in turn is a function of the spacing of the tie back and the soldier piles. The spacing is very critical in limiting the deflections. The tie back spacing, however, are generally limited to 4 feet because of the constructability and overlapping of the bonded zone for the tie backs. And especially in our case, the tie backs were in excess of 60 feet long, so we had to make sure that it didn't meander and conflict with each other. As far as constructability and flexibility, installation and locations in micropiles can be very flexible, and we can change during construction if there's any uncertain subsurface condition. Also, as we encountered, we were able to customize the system during construction when we encountered inaccurate as-built drawings. So with this, we figured that micropiles are a great solution to limited access and overhead clearance areas for support of excavation. And with this, I'd like to thank you. Any questions?
Yeah, if you've got any questions,
okay.
take them.
Thank you, Eric and Vivek. That was wonderful. If there are any questions, if you'd ask them through the portal. In the meantime, I was going to ask a question. Was there, with the amount of movement that the tracks experienced, was there a change in operations? Did it trigger some type of of a response by the train operators?
Well, the Amtrak had routinely run geometry trains every 2 weeks, and in some cases more frequently. And they knew the construction was going to happen here, so they did increase the amount of geometry trains they were running, and they did do a lot more maintenance on it as well. If you remember that graph where it really jumped around a bit, they were out there quite a bit doing a lot of maintenance. Some of it was kind of hand maintenance, but some of it was also the track tamper, where they actually pick up segments of track and tamp underneath it and so on. So Amtrak was keeping a real close eye on this.
Okay, Eric, are there any other questions that have been asked that you'd care to express to the group?
Yeah, one thing we like to do in general when we do this is we like to compare our predictions with the actual movement of the wall. In this case, and we were asked that at a conference when we presented this last year in North Carolina, and unfortunately we really couldn't do that in this case because it appears that the bulk of the movement was coming from the scour hole, not the wall. And Amtrak had maintenance crews had told us that this was a maintenance issue in that area, that they were spending a lot of time on maintenance in this area, but before we even started working on it. So so in this case, yeah, I would like to have compared the prediction to it, but our failure mechanism was a retaining wall. The real failure mechanism was something we didn't even think about, and that was scour.
Interesting. Okay, well, thank you guys very much for your presentation. Our next presenter is Lipton Carswell. Lipton received her doctorate from the University of Massachusetts Amherst in 2015, specializing in design and analysis of offshore wind turbine structures and foundations. She has continued to focus on soil structure interaction problems since joining the Boston office of Haley and Aldrich in September of 2015, working primarily on excavation support system design. Wystan, we'll turn the time over to you.
Thank you, Glenn, for the introduction. I'll be speaking to you all this afternoon about supportive excavation, wall, and ground movements. I'll begin by talking a little bit about why estimations of supportive excavation, wall, and ground movements are important, how these movements can be estimated, some benefits of using empirical correlations to come up with these movement estimates, and then spending most of the time talking about how supportive excavation performance in the greater Boston area compares to published literature. I'll end with some conclusions and takeaways, and you'll see the acronym SOE for support of excavation throughout this presentation. So why are estimations of supportive excavation movement important? Well, the thing that comes to most people's minds, and what we've seen in these previous presentations, the settlement of adjacent structures is typically a hot topic, and that's going to be important for any abutter to your excavation. Of particular concern might be high-rise or heavy structures, historic structures of cultural significance, and any structure that is within close proximity to your excavation. And lastly, critical public infrastructure. For instance, like we saw in the previous presentation, railways or perhaps highways, tunnels, things like that. Utilities can also be affected by ground movements. Significant ground movements can lead to interruptions in service. And the last point I have here is constructability for the permanent structure. So, for instance, if your supportive excavation wall is a concrete diaphragm slurry wall, it's probably also going to act as the permanent foundation wall for the structure. So the amount that it moves during construction is going to directly affect the rest of the structure and will be a concern for the structural engineer. So how can we estimate these movements? The movements themselves are a function of many different things. You know, I have some of them listed here on the left: soil, groundwater, the depth and shape of your excavation, construction method, you get the idea. And so there are different methods that take into account some, all, a medium amount of these things. The simplest of which is empirical correlations. So they're typically simple figures or plots or equations which require very little input from the user, and you can get an estimation of ground movements relatively quickly. However, they don't tend to take into account very many site-specific things. To do that, you would need to upgrade to something like a beam spring model, for instance, where maybe now you can take into account the influence of soil profile, stiffness of the wall, things like that. But it's probably also going to give you a limited picture of the movements at your site. For instance, you might get movement of your supportive excavation wall, but you might not get movement of adjacent foundations. To get that complete picture, you'll need something like a finite element model. And those tend to be much more time-consuming and therefore cost a lot more and require a lot of data to be done well. The point I want to make with this, however, is that each of these methods can be good and can be bad ways of estimating supportive excavation movements. It really depends on the phase of the project and project scope. So when you have all of these different methods, why use empirical correlations? Well, as I mentioned before, they're very fast, and that can be instrumental for early phase design, where perhaps it wouldn't be appropriate to invest time and energy in a model when design parameters are changing quickly. Additionally, empirical correlations are based on real project data. So they're not theoretical, they're based on observed movement from projects, which means that they're based on the good, the bad, and the ugly that happened within those projects. And that type of data aggregation provides you with a range of response. That response range can be useful for a number of things. For instance, if you have a wall that's already in place, it can give you an indicator of performance. Did the wall perform better or worse than you expected? And it can also provide a platform to communicate risk to your client. Some clients might care a lot about ground movements, and using an empirical correlation might give you the opportunity to suggest investing in that fancy finite element model. Alternatively, you might have a client that doesn't really care. Perhaps the excavation is in the middle of nowhere, a cornfield or a parking lot or some situation where large ground movements really aren't going to be a big deal. And also, because of the low investment for empirical correlations, they can be, and I would argue should be, used to calibrate or validate more complicated models, where depending on what you put in, it can be very easy to mispredict ground movements. So with that, I now want to focus on some of the experience H&A has had in Greater Boston's supportive excavation performance. Just to set the scene, we're talking about the city of Boston and the state of Massachusetts on the east coast of the U.S. Boston is a major metropolitan area with a dense urban landscape where ground movements are typically of great importance. We went through our project archives and for this presentation gathered data from 38 projects spanning from the 1980s to the present. But I want to go back in time now and start with Peck in 1969, who published this diagram showing settlement as a function of distance from the excavation. Both the X and the Y axis here are normalized by the depth of excavation. And then he divided it into three different categories, where category 1 is for sort of typical soils and average workmanship, and categories 2 and 3 describe situations where basal stability may be an issue. So that's those big global movements coming from behind the excavation causing bottom heave. These relationships were based on data from excavations supported by sheet piles and soldier piles and braced by crosslots, rakers, and soil berms. then, let's see, there we go. When we plot the Boston data on Peck's diagram, you can see that most of our data lands in Category 1. We've got some data in Category 2 and almost nothing, I think maybe one lonely data point in Category 3. We should note that the data presented here is primarily from concrete diaphragm slurry walls, so these are stiffer systems than what Peck originally was considering. Additionally, we've subdivided our data into data from different excavation sequences. Blue represents conventional excavation, and green is for top-down, where the permanent structure is also acting as the temporary supportive excavation. So you excavate for your first level of basement, for instance, then you pour your permanent concrete floor, then you excavate to the next level, et cetera. And because of that, that concrete floor provides a good, it provides diaphragm action, which is a little bit stiffer than a typical excavation system. And you see that in the ground movements. Those green dots tend to be clustered towards the top and are typically lower than the conventional blue construction methods. Flash forward 20 years, Clough and O'Rourke wanted to take a deeper look at what Peck put together, because since then there were improvements in construction methodology, including things like tiebacks and the use of slurry walls. So this is that same plot from before, only when Clough and O'Rourke looked at it, they decided that Peck's diagram was really most appropriate for soft to medium clays. So I'm now showing conventional and top-down excavations with just clay. And as we saw before, we're landing mostly in Category 1 and a little bit in Category 2. So if I wanted to come up with a quick estimate for a Boston excavation in clay, I might take the line between 1 and 2 to get a number. Or if I wanted to be a little bit more conservative, maybe I interpolate and pick some number about halfway between that 1-2 boundary and the 2-3 boundary. For stiffer strata, Clough and O'Rourke put together this plot that now has a new envelope range for excavations in stiff to very hard clay. So I've now further subdivided our data by both excavation sequence and also soil type. So on the left, I'm showing conventional excavation sequences, and on the right, data from top-down excavation. On the top, I've got excavations in clay, and on the bottom, excavations in till. And you can see that Clough and O'Rourke's envelope of these movements pretty much captures our data for either type of excavation sequence in till and for the top-down excavations in clay. However, our conventional excavations in clay have a lot of points that land outside of this zone. So this probably would not be an appropriate figure to use for that type of situation. And that's really what I want to bring home to everyone. It's important to know where these diagrams or equations come from before you use them and make sure that they are applicable to your project situation. Clough and O'Rourke also considered lateral movement of supportive excavation walls. So this plot is maximum lateral wall movement from the excavation, normalized by the excavation depth, and on the x-axis we have increasing system stiffness, which is a non-dimensional quality that includes wall stiffness and the average distance between bracing levels. Note that it doesn't take into account the stiffness of the bracing system. They also added contours of factor of safety against basal heave. And when we plotted our Boston data here, we see that most of the lines plot with a factor of safety above 2.0. And now I also want to note here, all of these projects are complete. They've been successfully delivered. And so this is really something that we're doing in retrospect just to take a deeper look. And with that, we notice that there's a good family of these dots that land with a factor of safety lower than 1.4. And when looking for points of commonality with these, they're mostly very large excavations, so 2 to 2.5 acres in size, which, of course, is not taken into account in this plot, but is the responsibility of the geotechnical engineer to consider when coming up with estimates for ground movement. I also want to talk a little bit about the influence of concrete diaphragm slurry wall installation on ground movements. For those who are less familiar, concrete diaphragm slurry walls are excavated sequentially in panels by a clamshell bucket under a bentonite slurry or a polymer slurry head. Once the bottom of excavation is reached, a reinforcement cage is lowered in, concrete is tremmied up from the bottom of the excavation while slurry is pumped off the top. While that slurry does a pretty good job keeping the panel excavation open during this construction process, it can't necessarily provide that same amount of lateral stress that the soil felt in situ. And consequently, that results in a stress release. And that stress release can be associated with ground movements. So we went back through our project to try to see how much movement could be attributed just to this installation process prior to the mass excavation occurring at all. And when we looked at this, we saw that, well, for points that are about 50 feet from an excavation and further, the results are within survey tolerance, so plus or minus 1/8 of an inch. However, if you're closer than 50 feet to your excavation, well, installation effects might be something you want to consider in your estimates. We divided this data up by deep and shallow foundations. And so when we took a deeper look at the deep foundations, because intuitively it made more sense that shallow foundations might be affected by this process, we see a big range in response. So you have some points that are right next to the excavation with almost no movement at all, and some that are just a little bit further away but show 3/4 to an inch of movement. So this might be the time that you would want to invest in a more complicated model to better understand the situation if you are lying within this range, to better understand your site limitations. So to conclude, empirical correlations are a fast and useful way of estimating ground movements, but you have to ask yourself, is this applicable to my project? We learned, for instance, that for conventional excavations in Boston clay, we should probably use Clough and O'Rourke's soft to medium clay plots, not the stiff clay plots. And construction method plays a significant role in ground movements. That top-down excavation procedure resulted typically in smaller ground movements than conventional construction sequences. Lastly, beyond 50 feet, ground movements due to slurry wall installation are typically within survey tolerance. But for situations closer than 50 feet, you may want to consider installation effects in your ground movement estimates. And with that, I will conclude and give a special thank you to Hugo Meggett in our Boston office, who did a lot of the legwork for going through our project archive to come up with the data for this presentation. And with that, I will take questions.
Okay, well, thank you, Wystan. Do you have any questions that you see that you'd like to answer at this point?
So one question is, what about excavations in rock or sand? You know, yes, I talked mostly about excavations in clay in this presentation. And so for sand, the PEC diagram that I first showed, actually, that category 1 would be applicable for sands. Alternatively, going back to that Clough and O'Rourke paper in 1990 would provide a lot of figures and relationships for excavations in different strata. Another question is, does increasing slurry viscosity minimize movement? That is a good question. My guess is that while theoretically, yes, increasing the viscosity might help a little bit, I don't think that it would help significantly. The kind of stress release that would be associated here wouldn't be easily made up by this kind of quasi-hydrostatic lateral pressure.
Okay, Wissam, are there other questions that you would like to answer? We have a few minutes.
Sure. How about one more here? What causes the range of movement for deep foundations? Well, that definitely depends on the specific site. It could depend on, the exact soil strata, the foundation types, and also the construction means and methods. That's where things like the amount of time, for instance, that an excavation remains open might play a significant role. So I don't think that there is a cookie-cutter answer for why, there is a significant range.
Okay. Okay, well, very good. Thank you so much for that presentation. Our next presenter is Liban Afi. Mr. Afi is the founder of Foundation Engineering Consultants in the state of California. He specializes in excavation support analysis, drilled pier foundations, and substructural engineering software. He's a licensed civil engineer in California and has authored 3 books. He was recently awarded a U.S. patent for a new method of supporting lightly loaded foundations and pavements on highly expansive soils. He is very interested in filling the practice gap between geotechnical and structural engineers when it comes to foundations and earth-retaining structures. Okay, we'll turn the time over to Liban.
Thank you very much, Glenn. Hi, everyone. And thanks for ASCE for putting this conference together. Today, we will be discussing a excavation support system beneath a 5-story building, and it was built in Berkeley, California. So my presentation will outline the building, site plan, the subsurface profile, the design of the shoring system at the restaurant site, and also the design of the underpinning system below the hotel side. And we'll have conclusions, and I will let you know the references I used. Also, hopefully, we will have some time for questions and answers. So the project is in Northern California in a city called Berkeley. And this was a mixed-use 5-story building. And the site, as you can see, is vacant. This is the view from the curb looking towards the site. And on the left side is a hotel, existing hotel that had to function. And on the right side is a restaurant building. Now, the hotel side gave us permission to do underpinning beneath their foundation. But the right side did not give us permission. So the architect was interested in having a 1-story parking garage below level, and he wanted to span all the way from beneath the hotel to beneath the restaurant. But because we did not have permission beneath the restaurant, we had to come just to the exterior face of the restaurant. And if you look at the site plan, you can see the proposed is the underground parking. It was mostly rectangular in shape. And on the above side of the map, you could see the ramp. That's where the curb they'll be coming in to drive to park. And in that one corner, you could see the existing hotel. And towards the lower end is the existing restaurant. Okay, so if you look at the street, there is the intersection of Grand Street and University Avenue, and the area marked outlined in red, that is the proposed site. The geotechnical consultant did 2 borings, They did one boring towards the rear side of the building and one boring towards the front side of the building. We will now see what the subsurface profile looks like, and this is taken from boring 1. By the way, boring 1 and boring 2 were very similar. They mostly comprised of very stiff to hard sandy clay, unconfined compressive strength values from a pocket penetrometer was from 1.25 TSF to 3.5 TSF, or those in SI units about 120 to 335 kilopascals. The minus 200 sieve was 53% passing, so it's barely cohesive material. They did do Atterberg limits, and the liquid limit was 40, plasticity index was 23, giving us a PI of 17. If we look at the geology at the site, and the site is mapped as alluvial fan deposits, and it's fairly uniform in this part of Berkeley. It's not the Berkeley Hills, but it's the level portion of Berkeley, level sites, flat site. So there were two geologic maps that were referenced in the geotechnical report. One was done by Radbeck in 1957, and it says that a Temescal formation was found, and this is mostly clay, gravel, sandy, and silty clay. And then there was a more recent geologic map by Witter in 2006, and it did classify it as late Pleistocene alluvial fan deposits, and it did say that it was still clay material. So when we did the design, we had to reference the geotechnical report, and from that soils report, we were given active earth pressure from the backfill side of 45 PSF per foot. We were given allowable passive resistance of 350 PCF, and we were asked to ignore passive resistance in the upper half foot. The passive wedge is it's a value that corresponds to the soil friction angle. So, for example, if your phi is 28 degrees and you multiply by 0.08, you get the passive wedge, which is in this case 2.24. And that's what the width of the passive resistance is below the excavation level. Because we're in California, the seismic earth pressure was just a simple 10H, and we had to consider surcharges. So we had two different surcharges. One is from the adjacent ramp. We consider that as 150 PSF. And then there were the building surcharge. One was right underneath the hotel, and the other was the restaurant. And for the restaurant, we used 2,000 PSF. And for the hotel, the travel lodge, we used 2,500 PSF. Now, let me go back a little bit on this passive resistance. We usually, when we design shoring systems, especially cantilever shoring, we have two passive that we usually get from the soils report. Either we will be given an ultimate passive resistance or we will be given an allowable passive resistance. Ultimate is just Kp times gamma. It's not reduced by any safety factor. Whereas allowable passive is the Kp times gamma, and then usually divided by something like 1.25 to 1.50 factor of safety. It's important when we design the shoring system that if we use the ultimate passive resistance, that it's usually a higher value because it has not been reduced by a factor of safety. Therefore, we increase the embedment depth by 1.4H. But if we're given an allowable passive resistance, then we find out what the embedment depth is due to calculation, and then we just use that because we were using a reduced allowable passive. We, in this case, for this project, used cantilever shoring software by soilstructure.com. Okay, so as a general guide to shoring, usually if the cuts are less than 15 feet, we can go with cantilever method. If they're taller than 15 feet, we go to a tieback or a brace system. And we're still seeing this depth of fixity approach in a lot of geotechnical reports. We like to see that this continued. It doesn't take into account the distributed nature of the backfill pressure and the distributed triangular load or trapezoidal load of the passive resistance. However, when you're designing cantilever shoring, you can use either the gross pressure method or you can use the net pressure method. And this ultimate passive, I just covered that earlier. So what does the gross pressure method and net pressure method look like? On the left-hand side, you'll see that the backfill pressure, which is the active pressure, goes all the way down to the pile tip. It goes beneath the depth of excavation, and it goes all the way through the embedment depth. And then on the passive side, it starts at the dredge line or the bottom of the excavation. That's called gross pressure method. In the U.S., we don't see a lot of that. Internationally, we see most of them use the gross pressure method. In the U.S., mostly we use the net pressure method, and that's where the backfill pressure goes down to the depth of excavation. In this case, it's 25 PCF, which is indication of very dense soil. And then a passive resistance starts at the dredge line, but we usually ignore a foot or up to 2 feet below the dredge line. When we look at the cross-section on the restaurant side, there was an existing footing that supported the restaurant, and because we were not given permission to go underneath, we had to go the soldier beam right adjacent to it. And because we did not want any sloughing, we decided to put the steel plate lagging right behind the rear flange. Okay. So the soldier beam and steel plate was used. The size happened to be W8 by 48, and we encased that in 18-inch diameter pier. And we wanted to control deflection. There was no guidance in the soils report, but, being litigious state, we kind of imposed on us to use a 0.1-inch maximum deflection, and that dictated the 4-foot spacing. Embedment turned out to be 8.5 feet, which is quite a bit for a 4-foot cut. It's more than double. And if we look at the plan view, you could see that the spacing of the piers, there is the wood lagging. That's not on the restaurant side. That's on the ramp side. And then you have the I-beams. The soils were very stiff. And as I said, the pile spacing was limited to 4 foot on center. And if you wanted to see what the piles look like on the restaurant side, that's the behind is the existing restaurant. And then in front, we placed our soldier beams at 4 foot on center. So now we go into the restaurant side. There is the I-beam, and this is the cross-section from cantilever shortened software. And if we look at the plan view, you could see that there is the I-beam, there is the 18-inch pier, and the program told us there is a 3.13-inch diagonal space. That means for construction-wise, when they drill this pier, they can easily lower the I-beam and they would not have any construction difficulty. If we look at the plots, on the loading side, you could see there is the blue line is the loading from the backfill, which is the active earth pressure, and then the red line is the passive resistance. The diagram to the right gives us the shear diagram, and by the way, we had to limit passive resistance to 3.5 KSF. After that depth, we had to stay at 3.5, so it became uniform. This is the moment and deflection diagram, and you could see that the deflection was less than the 0.1 inch that we wanted. Now we need to look at the hotel side. So this is the existing hotel, and because the architect wanted to expand, he wanted to have the I-beams right underneath the hotel. We were given permission. So if you look at the cross-section, we had to do a slant pile and then lower the I-beam and then push it back up underneath the existing and then connect it with anchor rods and fill it with concrete. So if you want to see what the plan view looks like, there is the Travel Lodge Hotel, and Soldier Beam 14 to Soldier Beam 18 are the piers supporting it. So these are really beam column. They're taking the axial load from the foundation, and they're taking the bending from the earth pressure. We had to use a spacing of 6 feet to comply with the 0.1-inch deflection. And here is what the cross-section is. The yellow soil is the backfill soil, and darker brown is the passive resistance. And when you look at the hotel side, we had to use 24-inch pier. 18-inch was too small, and we ended up getting another about 3-inch clearance on the diagonal. And similarly, if you look at the loading side, the blue is the backfill pressure, the red is the passive resistance, and the diagram on the right shows you shear. As you could see, in the lower 50 or 60% of embedment, there are no stresses. There are no shear stresses felt. And if we go into the moment and deflection, the same. You could see the maximum moment is like 2 or 3 feet below the bottom of the cut or the dredge line, and then the deflection again met the 0.1 inch. Now, because this was a rectangular site, we had to have I-beams all the way around, and this is the section where there are no structures behind. And about 18 months later, the building was completed, and this is what it looks like. Obviously, you cannot see the work, which is below ground. And in conclusion, I'd like to say for cuts less than 8 feet, even if we use them as underpinning, like a beam column, they can be designed as a cantilever shoring. But if they go much higher than that, like 10 or 12 feet, then we'd like to consider putting a tieback. When a neighbor doesn't allow the work under their property, it's typical to see that from time to time. We have to use closely spaced piles and limit our deflection to 0.1 inch. But one thing that helped us with this project is we had very stiff, cohesive soils. And for references, in designing this project, we used the ASCE steel manual, and there is a good book called Recommendations on Excavations by the German Geotechnical Society. And with that, are there any questions?
Well, thank you, Lipton. A very interesting presentation. Before we go to the questions, I had a question about how you were able to drive the piles immediately adjacent to the restaurant. There must have been some kind of an extension that you used on the pile head, or how was that possible?
Yes, because we had cohesive soil and we had existing structure, Glenn, we decided not to drive, but instead to do a drilling method. So we used an 18-inch auger and came right against because their property line ends at their outer edge of the footing. So we were able to come right at the edge and then drill 18-inch pier and lower the I-beam.
Okay.
So there were no vibration
Okay, very good. It looks like you've got some other questions. Would you like to answer those?
Yes. So one question I see is how do you ensure that the H-beams are centered within the borehole centralizers? Okay, there is a little giveaway, because when you look at when we do the design, we always try to limit our maximum bending moment to only 60% of the capacity. So that way we have additional 40%. So even though the design says 4 foot on center, if we end up having 4'3" or 4'5" on one pier and then maybe 3'9" on the other, it doesn't change. It's not that critical because the cuts were fairly low. So in this case, we did not have to worry about exactly being right in the center. And then how much actual building was observed? That's an excellent question. In this project, it was so fast-tracked. We submitted the plans Friday, and then the contractor called me Tuesday and said, hey, would you like to come and check? And I said, check what? He said, well, we're in construction. And so apparently they submitted the plans Monday, they got it approved Monday, and they went into construction Tuesday. So there was no opportunity to do site survey measurements. But with the cantilever shoring software, what it does is it doesn't use the depth of fixity approach to do the calculation. It uses the distributed loading method where we do a limit equilibrium. We have the backfill pressure, and we have the passive resistance, and then it takes the encasement of the concrete. So if we have an 18-inch pier and 4,000 PSI concrete, you'll see less deflection than if you had 2,500 PSI concrete with the same 18-inch pier. So, but because, as you can tell, 8 by 48, 48 pound per foot is kind of heavy, so there was no issue. There was no worry with the deflection.
Okay, it looks like you have another minute or two. Are there other questions that people have posed that you'd like to try to answer, Liban?
Yeah, so one of the methods that we usually see is, people always are interested in, well, how do you calculate your embedment depth? I mean, for cantilever shoring, do you use a cubic equation of the D? Do you use a quadratic, to the fourth power or so on? So we like to keep it simple. We see in the soils report backfill pressure, and we see passive resistance, and we just draw a triangle for the active and triangle for the passive if there is no cohesion. We don't factor the backfill pressure. And so if we get ultimate passive, we just multiply the embedment depth by the calculated depth by 1.4. And if we get allowable passive value, we don't multiply it. So that's one method. And the other method or recommendations I would have to new people coming into shoring design is try to use this limit equilibrium approach and not go into the lateral springs method where you have lateral spring, on the backfill side, lateral spring on the passive resistance. In between them is a gap, and the soil is more of a continuum. So we would like to stick with this old true and tried method of using limit equilibrium.
Okay, thank you.
One other question I see yes,
go ahead.
Yes, I see that. Thank you. Sorry. Was there any instrumentation? No, actually, this was the fastest job I've ever worked on. Literally, it took about 72 hours from the time we submitted the plans to the client to the time they went into construction. And that just kind of blew me away. So it's possible they had good relationship with the city, or it's possible everything else was done and shoring was holding up the project. We don't know exactly what happened. All I know is they went into construction right away, so we're not able to do any instrumentation or verify our deflection methods. But we do understand that they were happy and they went on with the basement construction as usual.
Okay, well, thank you, Liban, very much. A very interesting project. Our next presenter is Michael Sibley. Michael graduated from the University of Notre Dame with a Bachelor of Science and Master of Science degrees in Civil Engineering in 1973 and 1975, respectively. He worked for a geotechnical and materials firm in South Bend, Indiana during that period of time, and then returned home to the Pittsburgh area to work for a civil engineering consulting firm from 1975 to 1983. He then established a geotechnical engineering consulting firm named Earth Incorporated and actively serves as president some 33 years later. His work has transitioned from primarily commercial, municipal, and some residential to primarily public sector roadway and bridge projects, along with relatively large-sized commercial development, such as the 130-acre McCandless Crossing commercial development, highway bridge projects on Interstates 70, 79, 80, and 81, the Pennsylvania Turnpike Main Line, the Greensburg Expressway, the Beaver River Expressway, the Mon-Fayette Expressway, and the northeast extension of the Pennsylvania Turnpike. As Chief Geotechnical Engineer for Earth Incorporated, Mr. Sibley is responsible for the technical as well as administrative aspects of all geotechnical and supplementary civil engineering projects Earth Incorporated undertakes. And with that, we'll turn the time over to you, Michael.
All right. This project was, the owner was the Pennsylvania Turnpike, and we were doing our work for the low-bid contractor, Trumbull Corporation. Trumbull had enlisted us prior to bidding to look at issues or matters on the project, including the types of materials that would be getting into in excavation, what could they be used, the quality of any rock, what bidding advantage maybe they could have by spending a little extra time to understand what it is they were going to be digging and placing as fill. So as part of the job, which was basically widening the 4-lane Pennsylvania Turnpike, which had a 10-foot center median, they widened to 6 lanes and then increased the median from 10 feet to 26 feet. So it was uniformly widened, so it was widened about the existing center line. So what happened was we had already, prior to the bid, there was 2 retaining walls. One was about 740 feet, and it was the as-designed MSE wall. They did allow a T-wall alternate. No other allowed wall types were there. So we saw, with the fact that they were asking for this one wall, geez, if we could steepen the slopes and use select rock, that could save them some money. So indeed, that's what happened. The 740-foot wall was re-engineered, value engineering, with select rock, high-quality quarry rock, and so that's how that happened. About a week before the bid was due, there was another longer wall, 1,573 feet, and it also was designed by the owner and their consultant to be MSE wall, and because of this widening, this MSE wall was hanging down over the existing slope. Okay, so what that meant was you weren't able to take advantage if you were doing any kind of wall type structure, passive pressure resistance in front of the wall, as the 1.5 to 1 slope is 33.6 degrees, and the parameters we could use were those used in the original design, which was a phi of 32. So technically, if you tried to plug in passive pressure resistance, you'd actually get a negative number. So during the bidding process, we were asked to look at the quality of the existing fill to install temporary shoring through it. All right. So this temporary shoring was to be at the back of the wall. I've shown you the outline here. Introduction, then we get into design criteria. Connective strength of the interconnects of sheet pile wall, driving the sheet, some photographs from construction. We did get some stress measurements to compare to design, and then conclusions. So what you see here is part of the original design is and the bidding. This sheet pile wall was bid at, the MSE T-wall alternate was bid at $7.6 million. And the contractor estimated that it would take 11 months to do this, not just to build the T-wall, but to put in 1,573 feet of temporary shoring against active traffic that's as deep as 30 feet. So you build that, then you have to, you put in temporary shoring, then you have to turn around and start the wall. We came up with this concept to Trumbull of sheet pile wall with 3-way connectors, and basically we refer to them as fins, perpendicular elements to the face of the wall, which would basically serve as vertically planar tiebacks rather than discrete tiebacks. Okay, so that resulted in 5% savings, which was the minimum amount of savings that the Pennsylvania Turnpike would accept. So the contractor made those numbers work. The interesting thing here is that it only took 6 months to build this versus the 11 months that the contractor had estimated. So the height of the wall above the exposed slope is 21 feet. The sheets extend on that outer wall face about 31 feet deep. There was 2,000 tons of steel used. They were PVC sections, 26 pounds per foot for the front face, and in the fins, we used the same PVC sheets, 13 pounds. But nonetheless, over that length of close to 1,600 feet, you had 2,000 tons of steel in the ground. You'll see that we had 5,200 cubic yards of flowable backfill. The Turnpike has a Type C mix, and it's 300 psi, and that was put in the wedge between the wall face and the existing slope. And there was another 1,100 tons of coarse aggregate used in the wall construction. So as we move forward here, here's a picture of the as-designed MSE wall. To the left, down below on the slope, is a right-of-way line. We weren't able to consider with that right-of-way line there, we were not able to consider a steep slope. There was a stream at the bottom. There was just no room to try to make an earthwork solution to this. So you had to deal with a steep slope. At the back and the highway side of this MSE wall, they're showing a bolder, darker line, which is your temporary shoring. So ideally, that gets put in first, then you build the wall. Okay. This sheet pile wall idea, we basically took the same dimensions as the designed MSE wall. In other words, if we were going to sell this idea, we didn't want to show any deficiency in geometry. The width of the solution, we were going to the precise depth, the precise width. I mean, we're talking about within inches, figuring that if we tried to skinny it up with an idea such as this tied back sheet pile wall using vertically planar thin sheets, it would never sell. So we thought this was the way to go. The contractor we had worked with a number of times before, and in fact, the particular superintendent was receptive to different ideas, and it was just a good circumstance for us to have this man to work with. So again, 1,573 feet of wall. The spacing between the what we called the main fins, which constituted 4 sheets along the front face before you hit the next three-way connector, was roughly 9.5 feet. So that's 4 sheets. Each sheet's width is about 2.32 feet. And how does this wall work? Well, it basically works because of the friction or resistance, the soil-steel interaction, plus we considered the dead weight of the soil contained within the ins and outs, the Z shape of the sheet pile section. We use that weight as restoring moment to help bring down or to help contribute to the stability of the wall. Again, this wall was founded at the same depth as the MSE wall, and one key factor I mentioned, the quantities, was the cementitious backfill that was placed in the wedge between the wall face and existing slope. It would have been difficult, of course, to compact material down in that wedge. At first, the contractor was somewhat wary of the cost of that, but we told him that we really needed to do that for our comfort, that the material was going to be of sufficient integrity and not basically placed or dumped into place. It needed to be solid, as there was going to be a long pipe run, a storm sewer run along the entire length. So that's where the flowable backfill come in. That strength of that flowable backfill, that the fact that it would set up also has a real impact in that if material is set up, at least right at that wall face, that is not exerting any significant pressure on the wall. Part of the reason we were able to think of this idea is we had done work directly for the Pennsylvania Turnpike a few years earlier in which sheet piling was used as for some reconstruction. There was no widening of the template, but yet there was rubblization of pavement. The result is you raise the grade. You're on a very steep slope, 1.5 to 1. So cantilever sheeting was suggested for use with the turnpike. There was matters of permitting with wetlands at the bottom of the slope, and if you went with a fill, this would be an issue. It would delay the project by a year and a half, they felt, with getting permits through environmental permits. So it was just the fact that we had that prior experience with a turnpike on a sheet pile wall, which has never been used as a permanent wall on a turnpike. There was some level of familiarity and ideally confidence that what we were showing was something that reasonably could work. This is just showing a three-way connector where you have the wall face, you have the perpendicular fins. This was what was proposed. It's what the contractor, Trumbull Corporation subcontractor named Brayman, who actually installed the wall, what they wanted to use. But when it came time to, after getting this approved, that approval process, by the way, was 6 months. There were contrary opinions as to doing this. Could you meet a 1-inch deflection requirement? And the answer was basically no. Nobody would want to guarantee that if you're driving sheets and there's interlock, and with the interlocks, there's some play in those sheets. The fact that they went this route, they were buying into a relaxation of what you might call, what you would say is deflection, but in reality, what we were really after was a tolerance of where these wall face sheets would end up. We couldn't guarantee that we would be within 1 inch. You're driving on a steep slope, and the nature of that is if there's going to be movement, it's going to move in the direction of least resistance, which is the downslope. It's certainly not going to move really laterally or upslope. So we included a 2-inch tolerance, which ideally meant they had 4 inches to work with to get that wall face in the place. So this connector, as it was not accepted because it was not American steel. It wasn't American made. This was a Buy America project. So the only ones of that particular type that were available were foreign made. So before construction got going, there was some scrambling to find another American-made connector, and here you have, in a sense, there's 5 potential hookup places for this particular connector called SKPT. So that's what was actually used as part of the construction. Design criteria. These parameters here, existing embankment parameters, those were provided in the foundation report written for the MSE wall, and they included a moist density of 120 pounds cubic foot, saturated density 125, no cohesion, friction angle of 32 degrees. As I said, you can't really justify a 32-degree angle on an existing slope that's 33, 34, 37, 38 degrees, and that is, again, why we did not consider passive resistance in front of that structure. LRFD analysis all worked out well. We had excellent resistance in the pull-out, basically the tension capability of the fins 1.5 to a factor of 1. Overturning performance, 1.17. So that was another reason to just go with the as-designed MSE wall dimensions. If we tried to skinny that up, we would drop below a performance ratio of 1.0. Based on the LRFD analysis, the tension was 7.8 KSI. The allowable or permissible tension in steel in tension is 37.5 KSI for 50 KSI steel. In the wall face, we determined that we needed 11.4 inches cubed a foot of section modulus. The particular PZC 26 shape gave you 39 inches per foot. And by the way, even though the report, the foundation report, indicated that there was no corrosion potential in the existing fill material of the existing embankment, we did factor in a 1/16 inch deduction on each side of the sheet. The factor safety global, we exceeded the 1.5, which was the requirement for the original design. This just shows a true cross-section at the maximum height. The distance shown above the wall, above the 1.5 to 1 or steeper slope is 21 feet. It's buried another 10, and again, those dimensions were the precise dimensions width-wise that the original design used. There's a line there, a dash line, which is estimated top of rock. And in fact, they actually hit at the very back end, which was predicted based on the available test boring information provided with the design, that we would be close to the top of rock in that inside lower corner. And indeed, there was, out of all that steel, there was a few sheets didn't make it all the way because they hit bedrock. By the way, another factor, one of the reasons we felt that sheet piles could work here, in addition to the soil boring results seemingly indicating there were no boulders or cobbles that could inhibit advancing the sheets, was the fact that in the cuts, we're in residual soil bedrock, probably 98% of the rock material was shale or shaly. There was a few percent of the total excavation quantity that was sandstone, and we felt that that was as much reflective of what's in that fill, that is the adjacent cuts, as the test boring results were. As it was, they had no problem driving the piles, except obviously where they hit bedrock. This is just a graphic representation from the foundation report that shows test boring results. And basically, they had an N value of 50 and 25, and that's the material they were driving the sheets into. And so it turned out to be not an issue, that is the driving. As far as the analysis goes, this is the maximum height of the wall. This is from that particular cross-section. And how we analyze this, we assumed, of course, no passive resistance in front. We show an inclined angle there, and that's representing the active failure wedge. And that is significant in that anything to the right of that incline, 61-degree horizontal active soil wedge, could be used in the passive resistance to hold back that wall face. This next slide shows, and it's an ASCE reference, that the figure on the left is if you have a single anchor. The figure on the right is if you have multiple anchors for a wall. And what we did in that, basically, we had a continuous anchor we carried that the back of that pressure diagram down to the very bottom. You can see in blue, it's X'd out, and so we wanted to plug in a little, which resulted in plugging in a little more load than that figure showed. Trumbull Corporation had hired another consulting firm who is certainly familiar with the Pennsylvania Turnpike to essentially provide a peer review of our work, being that the idea was so different. They felt that it would help to have a company with a prestigious reputation with the Pennsylvania Turnpike to weigh in on what they thought of this idea. And they did agree with the idea. Their comment was the calculations that were done, that we had performed, were fine, but you really should also be considering stress concentrations. Basically, the flanges of the sheet piles, and this is some representation of the outer wall of the sheet piles, that is the 26-ton sheets, that the flanges don't receive so much stress, but as soon as you make that bend on the web, that's where you get high stress concentration. And it may be a little difficult to see if you try to go with a blow-up view, you may see, but the hotter colors are at that point where you go from flange to web, both for what we call the main fin, but we also had a mini fin. Our main fin included 13 sheets, which basically got us 31 feet back from the face. Again, that's what it took to develop the factor of safety for global stability of 1.5. But at those bend points, as soon as you leave the flange and get into the web, the stresses are high, and they're in the order of basically around the high 20s, 20 KSI for the completed product. So this is important in that once you got off the cantilever, that is the wall sheet was obviously at the top of the roadway, but then we had an inside sheet we referred to as a brace sheet that we tried to carry that as high as we could to allow for a reduced cantilever in that area. And so that kind of set the tone for what that stress was going to be. But interesting, in the finite element analysis, that stress kind of continued all the way down to the bottom of the sheets. And again, these sheets are buried 8, 10 or more feet. Okay, connection strength. Another thing that the peer review company wanted to feel comfortable about was the strength in the connections. And this is a mill test report that shows roughly the yield strength is like, it's hard, I can't read that right now, but I think it's on the order of like 90 or in the 90 KSI range. The tensile strength is like 108, okay? So it's interesting that on this report, these connections that were pulled in tension, you had a yield strength of 90. The fact that we had this interconnected, and what helped with selling to the Pennsylvania Turnpike the idea of doing a wall like this was that they had failures, several failures, with temporary shoring on other expansion projects where they widened the roadway to 6 lanes. So, and they really didn't want to see a failure, certainly of temporary shoring. So this idea came in at the right time where they were wary of that. In fact, the adjacent project to this one actually had a failure in a temporary shoring where they had to close down one of the lanes for a couple of days until they were able to rectify that. So they really wanted to avoid that because that really wreaks havoc with traffic. It can result in total closures of which they can lose tremendous amount of money in tolls in a day. So that was a good factor working to our advantage. The other thing is the contractor kind of stressed to the turnpike that by having this so interconnected with steel, if there were defects in the existing embankment, remember we're talking about 1.5 to 1 sloped embankments, you may have groundwater built up in them. The test borings indicated that was not the case, but you're never sure about these things. They felt that if there was a defect in the original embankment that may not have been reflected in any test borings, just the idea of having this tied together gives them some comfort. So it took some convincing on our part, on the engineering side, and the contractor's part on a more senior level, why this was an idea they should consider.
Michael, this is Glenn Anderson. You have approached, but we have very limited time, and you have some really interesting questions. Would it be possible for you to summarize in the next minute or so and then answer maybe one of those questions?
Okay. Well, basically, additional slides here show connector strength. Let me rush through this real quick. On the left is connectors before they're stressed, after stressing. It clearly showed that a ball and socket is better. It's actually being retained on two ends rather than one. The driving of the sheet piles, I have a really cool video here, but I guess we won't be able to show it. But this is worth looking at regarding the driving of the sheets. Real quick, here's some photos of what the installations look like. Here's an aerial. Again, that's like 1,500, 1,600 feet long. Here's a close-up. You can see all the steel in the middle of the picture. Here's the first group of piles. There's 13 sheets. 7 were driven first. The area that shows the flowable fill was to allow for the storm sewer run to be placed. Here's another shot of that cradle that allows for pipe placement or any utilities. Another shot. This is the mini fin I referred to. There's 3 sheets here that help hold the wall in check, the wall face. Another shot of the outside lower end. Connectors. This shows a 2-way. This is a 3-way connector there on the lower section. Another shot. This is the full 13 sheets in place. Here's right before they were putting the barrier moment slab in. There's the moment slab barrier. Here's the finished product. What's not in place is the pavement structure, okay? This photo is showing expansion joint here. That was a factor used to reduce impact on the actual sheet pile itself. So if accidents, you have an expansion joint to mute the effect. Stresses real quick. We had two vibrating wire gauges here right at the bend point, vertical and horizontal. We weren't expecting much vertical as it goes. Horizontal, we're 11. We don't have all the fill up to date, up to grade, but we're 11 KSI. There's some more material to do, but we should be well below the 18. Curiously, a vertical stress of like 25 or 26 showed up. This could be resulting in some defect or settlement in the fill area. I won't go through these conclusions, but basically I won't go through all these, but basically this wall works, is viable if there's a need to put in temporary shoring to protect adjacent highway or traffic. If you don't have that, there's no way that it's economical enough to compete. So anyhow, as far as questions.
Okay, thank you, Michael. You will be able to, everyone that has submitted a question has submitted with their email address, and so since we've run out of time and we need to get one more presentation, we'll hold off on any questions, and then you can, after the fact, Michael, you'll be able to respond to these people directly. Okay, our final speaker today is Justin Lewis. He's a graduate of the University of Illinois at Urbana-Champaign with a Bachelor of Science in Civil Engineering in 2007 and a Master of Science in Civil Engineering in 2008. He has worked with Hayward Baker for over 10 years after joining upon completion of his degrees. He has worked on a wide variety of technologies. Justin has held many positions, including field engineer, and project manager. He currently is the division manager for the Structural Support and Earth Retention System Group in the Midwest, with responsibilities for managing and supporting a talented team in building, designing, and managing earth retention and deep foundation projects. Particular areas of Justin's experience include jet grouting, structural and bottom seal, sheet piling, soldier piles and lagging, secant and tangent piles, internal bracing, tiebacks, driven piles, and micropiles. And with that, we'll turn the time over to Justin.
Okay, thank you, Glenn. So my presentation is a little less technical than some of the others and a little more focused on the methods used for a particular type of earth retention. So we'll jump right into it. The project in question is the Hammond, Indiana Sanitary District CSO and Basins project. This project originally came about due to a lawsuit filed by the federal EPA in 1993 under the Clean Water Act due to the CSO events that were occurring from the Hammond Sanitary District, as represented by the red arrows on your screen. These were existing mains that came in and overflowed into the Grand Calumet River. In 1999, the parties finally agreed on a settlement that resulted in this project, and the project finally took place in 2013 and 2014. The result of the project, as designed by Hubble, Roth, and Clark, resulted in combining the two force mains at Soul Avenue and Johnson Avenue into one force main, represented by the blue line here, and it would take the flows into a basin that could hold approximately 33 million gallons. From there, they could hold the effluent or hold the sewer water and pump it into the water treatment plant across the street, or in very extreme cases, when the basin would even fill up, they would experience a CSO event represented by the red arrow here. They felt as though the engineering showed that at the end of this project, CSO may occur, but the event should be reduced by up to 91%. So the particular portion of this presentation concerns the earth retention to take the combined force main underneath Calumet Avenue, located in the yellow circle here. So the soils presented at the site were the real difficulty in taking the force main through. So I kind of colored this here to try to help you see the different colors. The light brown kind of at the top and intermixed is mostly sand. The yellow, which is in a few borings shows up, is silt. And the brown is clay, and down towards the bottom we have a pretty stiff clay, the glacial till. But the black portion is really the problematic, and this is the organics and very, very soft clay. It could be best characterized, the area underneath the bridge, of having 13 to 16 feet of very soft organics, peat, and very loose silty sand with very high moisture content. So not great soil to be dealing with. The normal section for the combined force main involved driving sheet piles on either side, and there was generally a brace at the top for the cut, but the pipe was just placed in the hole and then strapped down for buoyancy purposes. obviously, due to the bridge, the sheet piles could not be driven or cannot be readily driven under the bridge. So the bridge component here's kind of a picture of the bridge, and here's the plan. What was proposed is you have the bridge here in red. The proposed plan was to drive two pits on either side of the bridge, a jacking and receiving pit, and then take the combined force main in this area through underneath the bridge, just using a jack and bore technique. All right, so this resulted in 160 feet of 120-inch, so 10-foot diameter, heavy wall, ASTM-C 361 reinforced concrete pipe. So very heavy-duty pipe. So here's what the as-bid plan actually looked like underneath the bridge. So you can see the bridge here. There were 4 piers, and then the abutments. The structure of the abutments is not shown, but 3 piers. The pipe actually went between the northernmost pier and the next one to the south, which was in the river here. So what were the problems? Obviously, we've explained some of them. The very weak upper soils may lead to a collapse in the leading face of the jack and bore operation. The jack and bore operation, the pipe was actually slightly smaller than the rest of the force main. So the smaller ID, and that was due to the thickness required for the jack and bore, and to resist buoyancy. So it resulted in a flow constriction. And then, frankly, it was very, very expensive to do this operation. So we came up with a value engineering alternate post-award. We were doing some other work on the project, and so we came up with a cut and cover technique. And we're working at 7 to 10 foot of headroom, so that may sound crazy, but in the next few slides, I just show you how we ended up doing it. So we obviously had the very, very weak soils with high moisture content, so water was going to be a large problem. So to combat that, we proposed a system of soil mixing and micropiles. So for the soil mixing, we would come in with our drill rig, working in the low headroom conditions. So you can see a picture here in the bottom right of the conditions. The drill would drill a row of soil mix columns on the south side, and then a row of soil mix columns on the north side. Using the same drill rig, we would then come back through and drill micropiles through the soil mix. So in this case, these were 9 5/8 inch micropiles. They were placed at 12 inches on center, so there was only a gap of approximately 2.5 inches between the micropiles. And they were installed along the center line of the soil mix columns being 24 inches, and then obviously the micropiles being the 9 5/8. So you can see here, actually in this bottom right picture that I have on the screen right now, you can actually see the micropiles. You can see the row of micropiles, so you can see how close those were. And then due to the depth of the cut, we needed to brace the top, which became a little bit easier with the micropiles in place, with simply using wales and struts across there. So here's what the finished product looked like. You can see here. You can see how dry it looks. I also here's a few more pictures of how it looks. One thing I'll point out so you really get a view of the different soil conditions. You can actually see the color change from the soil mix as it hit the glacial till. The soil mix tool could not actually penetrate the glacial till. It was so stiff, and so that's the very light gray soil you see at the bottom of the picture on the left-hand side. And then on the right-hand side, you get a perspective of the bridge overhead with the bracing and the whole trench coming through. So it looks very nice and dry, and for the most part, it was. Unfortunately, when the river comes up, even the best earth retention system is not gonna stop it. So we did have to wait for some time while the pit flooded, and then the general contractor had to clean it out. Well, I said that it was dry. There's some leakage, and for the most part, all earth retention systems will leak. You can see here, and represented by the arrows that'll come on the screen in just a second. You can see the ice formations forming. This picture was taken in the wintertime while this was open, and so the leakage, the minor leakage through the wall would build up as ice, and that actually created a little bit of an issue. What we found is that it almost created like a hydraulic jacking. So as the water would be able to penetrate in little crevices between the soil mix and the micropiles and expand, it would basically push the soil mix off. And then as the water warmed up, or excuse me, as the weather warmed up, it would actually kind of peel off the wall. So in order to fix that, we actually came back through, and it's kind of hard to see here, so I have an arrow pointing to it, but we actually had to come back in and put a layer of shotcrete to kind of hold the face together long enough for them to get the combined force main in. You can see here they're actually putting the force main in. They had converted this portion of the force main, and I believe the rest of it to actually a cast-in-place structure to save money as well. So then finally, the nice part about this system was while it's sticking up above grade while we were doing all the work, in order to finish this up and restore it back to grade, because we had the micropiles, all we simply had to do was come in, remove the bracing, and then we could twist off the micropiles, leaving the rest below grade. So you can see here a nice picture. You can see how close these micropiles were together. And in the bottom right, you can see a lookout where the bracing was sitting. So that's basically the gist of it. Like I said, I didn't get into much technical in that, but just wanted to show more of the method. And here is the final product. Obviously, the force main is buried, and there's no result. And the bridge stayed exactly where it was before we got there. So. With that, I'll see if we got a few questions.
Okay, well, thank you, Justin. That's very interesting. And yes, you have some questions. You have a few minutes if you'd like to take some time and answer them.
Yeah. So one question that was asked was construction dewatering required for installation of the 120-inch pipe? I don't know about the actual jack and bore operation. I don't know if they would have required any sort of dewatering or not. The system that we installed did not require dewatering because we actually coordinated to install the sheet piles to the east and west of the bridge into wet soil mix. So creating a fairly watertight connection. Obviously, nothing's exactly watertight, but water manageable. So there was no actual dewatering other than just some sumps that were within the trench. And then also have a question here. What did you use to stiffen the soil in the soil mixing? So I didn't get very far into an actual soil mixing operation, but what it actually consists of is using paddles that are injecting a cement slurry into the ground, and it mixes the soils that are in the ground with the cement slurry, and given some time, usually within 24 hours, it's going to start hardening just like concrete would, and will eventually harden even further. But it'll set up into like a soilcrete mix, which may be as low as 50 to 100 psi and maybe as high as 1,000 to 2,000 depending on the soil conditions. So here we weren't really looking for the strength out of the soil mix, just more of the water control. The micropiles are really doing the work. So, and then one more question that came in: why not precast segmental force main sections? I don't know. That was kind of beyond the realm of our operation. I think the precast was fairly difficult to get underneath the bridge, And I believe at the end of the day, the economics just determined that a cast-in-place structure was going to be faster to build. Originally, it was supposed to be precast pipe sections. So, Glenn, I think that's the questions I have.
Well, thanks, Justin. Are there any other questions that you think or that people have asked of you about this concept? Is this the first time you've used micropiles in the center of soil mix columns for structural support like this?
Yeah, so we've done similar applications, and one of the questions I get a lot is, what would you actually do different? You know, I described the problems we had with what I kind of term the hydraulic jacking or the ice jacking, and we have actually learned some lessons from this. We've done similar type applications, usually using jet grouting instead of soil mixing. We didn't feel the soils here were good for jet grouting, but what we would do differently is take the micropiles out of the center of the soil mixer, the soilcrete itself, because I think that created a lot of the problems. We would simply move them behind, or more likely kind of in front of the wall, to let it continue to be a continuous grouted mass for the water containment. And then so we weren't creating penetrations within that grouted mass, which I think is what really kind of created the problems, right? So.
Okay. Well, thank you very much, Justin, and we'd like to thank all of the presenters today. We think they did a wonderful job. We encourage everyone that has been online to think of projects that they've done that they might be interested in presenting next year in our conference. We'd like to also remind you that our gold sponsor, Keller, we're very happy to have them, and our two silver sponsors, Haley and Aldrich and Hayward Baker. And again, thank you very much for all of the time and effort done to put this together, and have a good day.